Now that we know a few things about limits and we know a few things about continuity, what I want to do in this video is I actually want to go through and construct an example of a limit problem that you might see in your calculus textbook. And I think that by constructing the problem, you'll get to not only see the thought process that maybe the textbook author had when they were writing the problem, but you'll also probably get an insight into how you should tackle all the limit problems in your textbook, and generally the best plan of attack for dealing with those problems. And also, I should say before I start, I know I'm talking a lot about if you have a calculus textbook, or if you're going through this with a calculus textbook, or if you're taking a calculus course at the same time. These videos should hopefully still be helpful even if you're not in a calculus course right now. And I think so. Hopefully, if you're not in a calculus course right now or don't have a calculus textbook, I'm not scaring you away at all, and you should still be fine. But I'm just saying, if you are taking a calculus course and do have a calculus textbook, we're going to construct something that you might happen to see in a limited problem. So anyway, let's go ahead and define a function. We're going to say that a function f of x is going to be equal to the function x minus 1. And actually, before I go any further, I'm just going to graph this. And this isn't going to be the complete version of what our function is going to be. And this is just a simple line. This is just a linear function, right? It's a function with a slope of positive 1, and we've got a y-intercept at negative 1, right? So we're going to hit the y-axis right there at 0, negative 1, and then we've just got a slope of 1. So if I can connect those lines like that, pretty much connect all of those crossings, and connect all of those lines down there, and that is our line. So now this is what this part of the function looks like. And I'm not done defining this function. I'm going to do one other thing to this function. And hopefully you're going to see that all I'm really doing when I do this is I'm going to multiply the function by 1. But I'm going to multiply the function by 1 in a very specific way. I'm going to multiply it by x plus 2 divided by x plus 2. And so hopefully you can see, if we were going to put 0 into this function, we have 0 minus 1 is equal to minus 1. And then 0 plus 2 is equal to 2 divided by 0 plus 2 is equal to 2. That's just like dividing by 2 over 2. It's just like multiplying this x minus 1 part of the function by 1. So we're really not changing anything by putting this onto our function. However, the only difference that this part of the function makes, is that now, because we're dividing by something, we're dividing by this x plus 2 term, it means that if we're going to plug negative 2, if we took f of negative 2, or if we took the number negative 2 and we plugged it into this function for x, that number is now going to be undefined. That number is now going to be undefined. And so we need to represent that on our graph. And the typical way, and we've seen this before, the way that we do that is we just have an open circle. So I'll just erase that point right there. We have an open circle at the point of where x is equal to negative 2, to show that we have defined values for every point around x is equal to negative 2. But right at that point where x is equal to negative 2, we do not have a defined value for our function there. So anyway, and hopefully you can see where this would be if we did have a defined value. It would be just the same exact thing as plugging in the value negative 2 into our function x minus 1. And that value should, if it were defined, it would just lie right along this yellow line, right along this line that we've already drawn for our function. So now I'm actually just going to multiply these two terms in our numerator together to get sort of the final version of our function. So let me write that down. Say f of x is equal to, that's x squared, and we've got plus 2x minus 1x. So actually, let me just go ahead and write. So if we multiply those two terms together, we get minus 1x, and if we multiply those two terms together, we get plus 2x. So that's plus 2x minus 1x. That's just going to be plus x. And then if we multiply together minus 1 and positive 2, we just get minus 2. So that's the numerator of our function. And in the denominator, we don't have anything besides this x plus 2 term. That x plus 2 term just stays the way it is in our denominator, x plus 2. And so now, let me say that, so this is now what we're going to define our function as. This quadratic function in our numerator and this linear function in our denominator. So this is, I'm saying, a linear function, and hopefully you've heard that term before, but this is just a typical function that we've seen before in algebra, where we have x, we have some slope on our x term and some y-intercept. This is in, I guess you could say, mx plus b form. That's what I mean when I say some linear function. So now let's say we were taking the limit of this function. We're taking the limit, and we were looking at this value. We were looking at this value where our function approaches negative 2. So the limit as x approaches negative 2 of, I'm just going to write this in yellow again, of x squared plus x minus 1, all of that divided by x plus 2. And now, hopefully, if you're taking a calculus course, which again, you don't have to be to watch these videos, but if you're taking a calculus course or have a calculus textbook or do a Google search for limit problems, you'll probably find something that looks a lot like this. And we can kind of see how we got this problem, right? We took a very easy function, a very typical function that we're really pretty good with dealing with right now. This is a very typical line function. We know it's a slope with, it's a line with the slope of 1 that hits the y-axis at negative 1. And all we really did was multiply it by 1, and we kind of got this complicated function over here. And so this is probably, if you're looking at an example like, or if you're looking at examples of limit problems, you're probably going to see things that look an awful lot like this. And so, if you remember from the past videos, what we're asking with this notation, the limit as x approaches minus 2 of x squared plus x minus 1 divided by x plus 2, we are asking as x gets really, really close to minus 2. So as we get really close to minus 2 in the negative direction and in the positive direction, what does our function approach? And we can see by the graph right here that our function is going to approach minus 3 right there. So we can sort of already tell what the answer is going to be. And so let me, I guess, show you analytically how we would go about solving this problem. And even, I guess we already did the work and kind of showed you where I got this this quadratic function in our numerator. We got this x squared plus x minus 1 in our numerator. So I'm just going to go ahead and undo that real quick. In a future video, I'll show you very specific ways of tackling if you don't know how to factor an x plus 2 term, or how to factor terms out of quadratic functions like this one, like our numerator here, out of these quadratic functions. I'll go through some really specific ways of how you would do that in the future. For right now, let's just say that this is going to be equal to the limit, and I'm just going to factor these terms out real quick. The limit as x approaches minus 2 of x minus 1 times x plus 2 divided by x plus 2. And so now you might be asking, well, can we cancel off this x plus 2 term in the denominator and the x plus 2 term in the numerator? And here, keep in mind that when we defined our function f of x as x minus 1 divided by x plus 2 over x plus 2, we know that this function, anytime, if we wanted to define a completely equivalent function, we know that minus 2 has got to be undefined on that function. But keep in mind, in the limit, we don't care about having that point defined. All we care about in the limit is that every single point, we just care about that the point that we are looking at is approached in the limit. We don't care at all what the function actually equals in the limit. So even though we're going to get a 0 term down here, it's perfectly fine to just cancel those two terms off in a limit. And that is what you are really going to be doing 90% of the time that you're doing these limit problems. You're going to be factoring something out of a numerator that looks exactly like what's in the denominator, or looks exactly like what's in the denominator that's making the denominator be 0. And you're going to cancel that off with a term in the numerator, and then you're going to be able to say that this whole thing is equal to the limit as x approaches minus 2 of just the function x minus 1. And so now we know what this function x minus 1 looks like. And we know, very importantly, that this is a continuous function. This is just a line, and there's no reason we can't plug any value we want into this function for x. And also, because it's a continuous function, it's just a continuous line, we can say that, fitting with sort of our definition of continuity, that every single point along this line, any point that we choose, including at x is equal to negative 2, we could say that any point along this line is approached to by the previous point and is also approached to by the next point on the line. So this is a continuous function, and there's no reason that if we wanted to figure out, well, what does the function approach as we get really close to negative 2, there's no reason that we can't just plug in negative 2 and evaluate the function at that point. So that's, and you're going to see when we do more of these limit problems, that's what you're going to be doing all the time. So let's just go ahead and say that this is going to, I'm going to actually be dropping the limit here. So this is going to be equal to the function if we just plug in negative 2 minus 1. So this negative 2, this was our x term up here. So we've just plugged in negative 2 into that term because we've said it's a continuous function. There's no reason we can't just plug negative 2 into that x term and see what the function is approaching at that point. And so then we get the answer that we're expecting to get. We get this function is equal, or the limit of this function as we get really close to minus 2 is equal to negative 3. And also, hopefully you could see that we did a lot of work, or we did some work in this problem. But really, when we graph this function, and this graph with this open circle at the point where x is equal to negative 2, hopefully you can see from this that we sort of already knew what the answer would be. We already knew that the answer would be minus 3 because that's what the graph is approaching. And I'm definitely going to talk about this much more in the future, but really I would say 90% of the problems that you're going to see in a first-year calculus course can be answered by sort of taking a look at the graph. Anyway, I'm almost out of time, so I'll definitely talk about that much more in a future video. Hopefully that gave you a little bit of an insight into how the limit problems are created in a calculus textbook.